my project is on guided synthesis of MRI images using conditional generative adversarial networks. So the motivation here is that MRIs along with PET scans are really common image modalities used to assist with the diagnosis of Alzheimer's, but it's hard to train a good classification model due to issues with data privacy and data scarcity, and such data quantity and privacy and scarcity issues exacerbate even further like class imbalances in terms of like how many of the samples you have access to, how many healthy brain samples do you have, how many mild cognitive impairment samples do you have, and how many full-blown Alzheimer's samples do you have. So the sort of idea or problem statement is that I want to use conditional generative adversarial networks to targetedly synthesize images of varying degrees of cognitive impairment from healthy to Alzheimer's to help shore up class imbalances and improve classification accuracies. So a breakdown of the tasks for my project is task 1, I need to construct a conditional generative adversarial network. Task 2, I need to use this C-GAN to generate images of brains with varying degrees of cognitive impairment, which I'll talk more about how I define these or categorize these degrees. And then task 3, to verify the quality of my generated images, I'm going to find baseline classification accuracy on my data set of images. And then I'm going to compare with the classification accuracy of that original data set and then concatenate with various image classes from my generated images. So a refresher on conditional GANs, if you aren't that familiar with them, is that they're really similar to the original generative adversarial network structure, with the real change being there's a label component added as an input. The labels can be as simple as like a class label or a classification, or as complicated as an image from an entirely different modality if you want to train the model to do like cross-modality imaging. So the way it works is these new labels are fed as input to both the discriminator and the generator to guide the behavior of the two models. When the discriminator gets the labels, it concatenates it with the inputted real images or fake images as sort of guidance to say this stack of images, if it's real, it should also be similar to whatever features are present in some given set of labels. Whereas when the labels are passed to the generator, they're concatenated with the sort of latent space input, which is used as sort of that noise you feed into the generator where the noise is then worked into the generated image. So you add the labels there to sort of help guide that generation of the image towards the appropriate label. And here's a block diagram of this architecture from the original paper, Conditional Generative Adversarial Nets. This Z is the noise input, this Y is the labels. Here's it getting fed into the generator. And then this X is a real image, and this Y is a label, and here's it getting fed into the discriminator, the way it's combined, and then you find the discriminator output. So the data set I'm using for this is OASIS 1. It consists of 434 MRI images from 416 different subjects of a really wide range of ages. So there's actually a couple of different image types available here. There's stacks of raw MRI slices, and then they did us all the favor of adding processed versions of these slices where they're averaged into one and combined and then skull stripped, which is really valuable if you're not familiar with what that means. It's where you take the MRI image and you mask out or filter out the rim area where the skull is present, so all you get is the brain. And then they also do stuff like do brain tissue segmentation to sort of highlight the edges within the brain. And I found that using images that were segmented helped with training the generator. So this is a pretty small number, just 434 images, but I was able to work around issues with the generator not being able to, or where the distribution of images wasn't wide enough to keep the discriminator from just easily figuring out what the real images were and what the fake images were. So to work around that, I would augment the images using techniques presented in this paper, differentiable augmentations for data efficient GAN training. So back to the data set, there's a lot of supporting information on subjects like age, race, gender, handedness, but the only one of them I really found useful is the clinical dementia rating. That's determined by the people running the study for OASIS 1, and the breakdown is that from 0 to 0.5, where the border is not included, you are considered cognitively normal. From 0.5 to 1, you are considered mildly cognitively impaired. And then from 1 to 2, you are considered moderately cognitively impaired. So by using that definition that they provided, I was able to split it into a multi-class problem of 3 different classes to generate images for. And here's an explanation of that. Here's a sample of like one of the images. This is an image that's an average of the raw slices from an MRI, but as you can see, it hasn't been skull stripped. And here's a version that has been skull stripped and segmented to sort of highlight the edges between the different parts of brain tissue. So here's a really primitive diagram of my architecture. There's this noise space or the latent space, and I feed in the label. I pass that to the generator. I get a generated image. That generated image is passed to the discriminator along with the label. In the same way, the real image is passed to the discriminator along with the label. And I then calculate losses on the discriminator for the real images and the fake images. And I use the gradients from that and back propagate to the generator and discriminator. And the target is to get a 0.5-ish loss for the discriminator, because that means the generated images are good enough that the discriminator is more or less guessing as to whether or not it's a real image or a fake image. So in terms of the actual settings for my training of the generator and discriminator, I used a learning rate of 0.0003 for the generator and 0.0001 for discriminator. These are asymmetric because I found while training that the discriminator was a lot better at its job than the generator was. And I think that's just because classification is an easier task than generating. I also used a non-saturating version of generator loss that is explained in the paper Generative Adversarial Networks. So the main idea there is that if you use the traditional loss as presented, the first couple runs of generator versus discriminator, the loss of the discriminator will be 0 or nearly 0, which doesn't give the generator any useful weights to work with when the gradients are passed backwards. So by using this non-saturating version, you avoid that problem with passing a bunch of zeros, and it helps the generator learn in earlier steps. For the discriminator, I just use a simple binary cross entropy loss between the output of the discriminator of 0, where it's either 0 to 1 with a stack or a list of either all ones for the real images or all zeros for the fake. So that's basically telling the discriminator that when running real images, you want to predict all of them as real, and when running fake images, it should predict all of them as fake. I train it for 200 epochs on an NVIDIA GeForce RTX 4090. It takes around 20 minutes. And here are some results. First, here's the loss curve for the discriminator over 200 epochs. You can see here at the beginning, the loss for the discriminator is nearly 0. It's doing really well, but as time goes on, the generator catches up and sort of surpasses the discriminator. But then right around the halfway point, the discriminator starts to catch on to what the generator is doing, and it evens out right around 0.5. So here on the left is a real image, and here on the right is a generated image. The colors are off. I think I have to re-normalize it due to the way the image's pixel intensities are transformed when passing to a tensor. I think I need to undo that normalization to put it back within this grayscale range, but the actual features of the image line up pretty well. So now that the task of constructing a C-GAN and generating image with it are done, the last things I have to do for my project are I need to calculate base classification accuracies on my MRI data set. I need to generate batches for classes, and I need to do the observation of the effects of those classes on classification accuracy. And those are my references.